Have you ever looked at a physics textbook and felt like it's written in a totally different language? Well, here's the secret. It kind of is. But the good news? The alphabet is incredibly simple. Today, we're going to learn that alphabet. And once you do, you'll have the key to decode pretty much everything. So let's jump right in. Okay, picture this. You're staring at a ridiculously long and complicated physics equation. What if I told you there's a simple trick, a kind of secret spell checker, that could tell you instantly if the whole thing is wrong without doing any of the hard math? Sounds too good to be true, right? Well, that's exactly what we're going to uncover. So where do we even begin? We start at the very, very beginning. You see, all of mechanics, the study of how stuff moves, is built on just three fundamental ideas. Think of them as the ABCs of the entire physical world. And here they are. That's it. Just three letters. Seriously, everything we can possibly measure about motion comes down to some mix of length, which we'll call L, mass, which we'll call m, and time, RT. This is the entire alphabet we're going to need. All right, so we've got our letters. What's next? We start making words, of course. We're going to start combining these fundamental dimensions, our L, m, and t, to describe more complex things, like speed, acceleration, and even force. Let's start with one we all know, speed. So how do we define it? Well, it's just the distance you travel divided by the time it took you to get there, right? So if we translate that into our new language, distance is a length, L, and time is just time, T. So the dimension of speed is L over T. And just like that, we've written our first word in physics speak. Simple, right? Okay, let's build on that. What about acceleration? Well, that's just how much your speed or velocity changes over time. We already know the dimension for speed is L over T. So for acceleration, we just divide that by time again. That gives us L divided by T again, which is just L over T squared. See how this works? Each new word is built using the ones we already know. It's like building with Legos. You ready for a bigger word? Let's tackle force. I know, it sounds way more complicated, but you'll see it's just another combination of our three simple letters. Let's see how they snap together. This breaks it down perfectly. We start with that famous equation everybody knows. Force equals mass times acceleration. F equals ma. We already know the dimension for mass is just m, and we just figured out that the dimension for acceleration is L over T squared. So what do? We just multiply them together, and we get the dimension for force, m times L over T squared. Just like that, a huge concept like force is translated into our simple alphabet. Okay, remember that spell checker I was talking about at the very beginning? Well, this is it. This is the moment. This whole process, which has the fancy name dimensional analysis, is our secret weapon. It's the ultimate tool for checking if an equation in physics even has a chance of being right. All right, let's put this thing to the test. Here's an equation that someone might claim calculates the final velocity of an object, but is it right? Let's put on our detective hats and use our new tool to investigate. The big question is, do the dimensions on the left side of the equal sign match the dimensions on the right side? Let's break it down piece by piece. On the left side, we've got velocity. We know that one. Its dimension is L over T. Easy. Now, on the right side, we're trying to add two things together. The first term is also velocity. L over T. So far, so good. But wait a minute. Let's look at that second term. We've got acceleration, time squared, times time. Acceleration is L over T squared. If we square that, we get L squared over T to the fourth. Then we multiply by T, which cancels out one of the T's, leaving us with L squared over T cubed. And there it is, busted. The formula is dimensionally incorrect. It's asking us to add a velocity to whatever L squared over T cubed is. It's literally like trying to add apples and oranges. You just can't do it. Because the dimensions don't match, the equation has to be wrong. And here's the amazing part. We just proved this formula is total nonsense without doing any complicated math. That's the power of this spell checker. Okay, so this language is fantastic for checking our grammar. But what's it actually good for saying? Well, this same need for precision is the key to accurately describing how things move in the real world. Let's look at a couple of key ideas. First up, let's clear up two words that people mix up all the time: distance and displacement. Distance is the total ground you cover. Think about the odometer in your car on a long, winding road trip. But displacement,
That's just the straight line change in position from where you started to where you ended. It doesn't care about the scenic route you took.
And that same idea applies to velocity. For that whole road trip, your average velocity is your total displacement divided by the total time. Maybe it was 60 miles per hour. But your instantaneous velocity, that's what you see when you glance down at your speedometer. Right now, you're going 72. That's the snapshot in time.
Now, let's circle back to acceleration, because this is a big one. In physics, acceleration is any change in velocity. And that's the key. It's not just about speeding up or slowing down. Think about it. If you're in a car and you take a turn at a perfectly constant speed, you are still accelerating because your direction is changing, and direction is part of velocity.
So you can think of it like this. Stomp on the gas pedal, that's positive acceleration. Slam on the brakes, that's negative acceleration or deceleration. But what about an apple falling from a tree? It speeds up, right? But it does so at a perfectly steady rate. That's what we call uniform acceleration.
So, we've learned an alphabet, we've built some words, and we've used them to check our work and describe motion. But why is this foundation so incredibly important? Well, because getting this part right, it's everything in physics.
Let's just quickly recap the whole story here. We found out that the universe speaks a language with a ridiculously simple 3-letter alphabet: length, mass, and time. We learned how to form words with those letters, and then how to use the grammar of that language as a killer spell checker for our equations. And we saw why being super precise with our definitions is the only way to really describe the world.
And look, this isn't just some abstract classroom exercise. Mastering this fundamental language, it's the very first step. It's the key that unlocks our ability to describe, predict, and understand everything in the cosmos, from the simple act of an apple falling to the ground all the way up to the majestic dance of galaxies across billions of light years.
So it kind of leaves you with a final thought, doesn't it? If the unbelievable complexity of the entire physical universe can be broken down into a simple alphabet of just 3 concepts, what other complex systems out there, in biology, in economics, maybe even in our own behavior, are just waiting for someone to come along and discover their simple fundamental alphabet?